Good day, everyone. This is Professor Friday coming at you one more time. Today we're going to be talking about a concept from linear algebra known as linear transformations. So first and foremost, we should go about the two big properties of linear transformations. So we'll start with the definition. We'll let T take us from a vector space V into a vector space W. These are referred to as the domain and codomain of a linear transformation. And we'll let that be a mapping, which simply means, when I say mapping, it means we're going to input a vector from the vector space V, and we're going to output a vector in the vector space W. Sometimes these are the same vector spaces, so it's not really that big a deal. T is considered to be a linear transformation. Oh, that's an important one. Let's underline that one. T is a linear transformation if it contains two additional properties. So the two additional properties that this has to contain is that if I take the sum of two vectors in V, which we know by the closure axiom is another vector in V, and we send it through our transformation, that the result is going to be the same as sending both of those vectors through the transformation T, then adding them together. We have a special name for this. We say that vector addition is preserved. So, whether I'm adding the vectors in the vector space V and then sending them through the transformation, or sending them through the transformation into vectors in the codomain W, then adding them together, that order shouldn't matter. So it's basically like a little order of operations property that's going on here. Excuse me. Property number 2 states essentially the same kind of thing, except that it is with regard to scalar multiplication. So if I have a vector U in the vector space V, and I multiply it by a scalar C, then I send it through the transformation, that would be the same as if I had sent U through the transformation T first, then multiplied by the scalar C. For this one, we say, oops, that's not how you spell scalar multiplication. We say scalar multiplication is preserved. So the big question to pose as we work through this is, how do we verify that a given transformation is a linear transformation, or how do we verify that something is not a linear transformation? So for that, let's try out an example. I've been giving this one some thought earlier today. I'd like to consider the transformation T that takes us from the set of two-dimensional Cartesian vectors into the set of three-dimensional Cartesian vectors. And let's define this vector, or this transformation, by the following. So T of, let's see, for a vector in R2, it would have to have two components. And we'll define this vector by, the output has got to be a vector in R3. The first component is going to be the sum of those two. The second component is going to be the difference of those two components. And the third component, let's make the product of those two components. So the question we get to pose is T linear? If so, verify why. If not, let's figure out why not. So first thing I'd like to do, just for funsies, my students know that I like to do things for funsies. So we'll say for funsies, I would like to calculate a couple of images. An image is the vector in the codomain that results from sending a vector from the domain through the transformation. So what I'd like to do is, this one's dedicated to Jim Carrey. Let's take the vector 2, 3 and send it through the transformation. So the first component of the vector is going to be the sum of the two components. Then we get the difference of the two components, and then we get the product of the two components. So the question becomes, what is the image of this vector? Simplifying all three of these, oh boy, pretty sure I can do this without a calculator. we get that the image of the vector 2, 3 through this transformation would be the vector 5, negative 1, 6, just to give you an idea of what an output is going to look like. So let's leave this on screen. Yep, like that. And then, there we go. I think that works. So now we'll go back to the question at hand and say, is the transformation linear? Now, in order to verify the properties of linearity, we have to do it as generally as possible. So first thing I'm going to need is two generic-looking vectors that are both in R2. So I'm going to take the vector x, and I'm going to say that that's equal to the vector with components x1 and x2. Then I'm going to take the vector y and say that that's equal to the vector with components y1 and y2. To analyze our first property of linearity, I'm going to have to take the transformation of the sum of those two vectors. 2 plus y1 comma y2. And we're going to have to pose the question, is that the same as the transformation of x1, x2 plus the transformation of y1, y2? Note the use of the question mark over the equal sign, since I'm not really sure whether or not this is true yet. So let's go ahead and add these two vectors together in R2. We can assume, unless otherwise indicated, that it will be standard operations. So the way that we add two vectors together in R2 is we add them together component-wise. We'll, over on the right-hand side, a change isn't necessary yet, so I'm just going to leave it as is. y1 comma y2. Okay. Now that everything is in the form T of something that's about to take place, I'm going to head back up to the definition of what our transformation was, which was take the first component plus the second component, that'll be the first component of the result. First component minus second component, that'll be the second component of the result. And first component times second component will become the third component of the result. So with that in mind, let's transform these vectors. So first component is supposed to be first component plus second component, like so. Let's throw some parentheses in here just for good measure. Second component, after we send it through the transformation, is supposed to be first component minus second component. And then finally, the third component is supposed to be first component plus y1 times the second component. Oh boy, that's a good looking vector. I guess that outside set of parentheses, oh yeah, that's totally necessary to make sure that it's still a vector. Now, that's all what the left-hand side is transformed into. Indicate that that's the left-hand side. We also need to look at the transformation of the right-hand side. So let's transform these two given vectors. So once again, it'll be first component plus second component, first component minus second component. Wait, no, x2, sorry about that. And then x1 times x2. Then we are adding to that the same thing for the transformation of y1. That'll be y1 plus y2, y1 minus y2, followed by y1 times y2. So that was the right-hand side after it had gone through the transformations. So a big thing to note here is that the right-hand side of the equation is now adding two vectors together in R3, whereas back here we were adding together vectors in R2, which is how we came up with what we came up with here. So now we get to pose the big question, is the left-hand side equal to the right-hand side? Well, let's find out. Left-hand side, when we're adding these things together, I guess it's not really necessary to have parentheses around them. But for the second component, we have that extra negative sign, so the negative sign will distribute through. So we get an x1 minus x2 plus y1 minus y2. The reordering there doesn't really matter. Then we have an x1 plus y1 times x2 plus y2. My favorite four-letter F word is going to pop up there. That'll be FOIL. So if we FOIL these together, that'll be x1, x2 plus x1, y2 plus x2, y1 plus y1, y2. That is our new left-hand side. The question is, once again, is this equal to the right-hand side after we add these together? So again, we're adding together vectors in R3, which means that we'll be adding them together component-wise. So we add the first components together. We'll get x1 plus x2 plus y1 plus y2. Then we add the second components together. We'll get x1 minus x2 plus y1 minus y2. Again, that's for the second two components. For the third two components, we're adding together x1, y1, x1, x2 plus y1, y2. Now we're still not really sure whether these two things are equal to each other, so we need to give a quick test. So let's check the first two components. Is it true that the first two components are equal to each other? Doing a quick analysis, x1 plus x2 plus y1 plus y2, all the components are there. That one checks out. For the second component, we have x1 minus x2 plus y1 minus y2, x1 minus x2 plus y1 minus y2. Those are also equal to each other. That one checks out as well. But as soon as we get to the third component, I see that we have an x1, x2, we have a y1, y2. Those are the same as in our second, or our right-hand side, but we get these two extra terms in here that indicate, no, these things are not equal to each other. Oh yeah, I should probably make sure that that is all on camera. Ha! So, at that point, as soon as we see that two of these components are not equal to each other, we know that our transformation fails one of the properties of linearity. As soon as one of the properties of linearity fails, we can say, therefore, T is not a linear transformation. T is not a linear transformation, so that does not work out for us. So, I think in the next example that we do, we should probably investigate something that is a linear transformation so that we can see what the checks would look like. Be back momentarily.